on, well, not easy, but certainly more classical tools in convex analysis and in Hilbert space analysis, namely the existence and uniqueness of gradient flows of convex functions on Hilbert spaces. So the theorem for us is the following: for every f in L2, there exists a unit curve with values in L2, which is continuous on the whole half line, and absolutely continuous in the open half line. So a priori, one might lose absolute continuity in 0, such that well, f times 0 is our given initial datum, and dt of ft is equal to the Laplacian of ft for almost everything. Right? And in fact, we have seen that for every t positive, moreover, for every t positive, the limit as h goes to 0 from above of ft plus h minus ft divided by h equals exactly the Laplacian of f times t. Right? So I can get an improvement from almost every to every, provided I take the right derivative. All right. Very well. Now let me start collecting a couple of easy to prove properties of this. Okay, of course, I'm very tempted to call this the heat flow, right? What else? But I already called the heat flow the other guy. So for the moment, I will resist this temptation, the gradient flow of the relative entropy. And let me just list a couple of properties. For ft as above, we have so first of all, well, actually, let me assume for simplicity, assume that our metric measure space, let me exaggerate with the assumption, is so that the reference measure M not only is probability, but it's a probability measure with finite second moment. If you wish, X is compact. Okay. Then for this and a flow ft or a curve ft as in this previous statement, we have so first of all, mass preservation. That is to say, the integral of ft, the m, is the same as the integral of the original ft for everything. This makes sense, of course, because m is probability measure. So a function which is in L2 is also in L1, and the integral is well defined. Weak maximum principle. So if f is greater or equal than some constant, or less or equal than some constant, then ft is greater or equal than the same constant, less or equal than the big constant, for every t positive, m almost every. Upper and lower bounds, either taken alone or jointly, they are preserved along this flow. All right. And finally, 3, entropy dissipation. Let's say that f, the original f, as is bounded, and let u be a function from capital C to R, let's say smooth convex, well, just smooth. Okay, then I take the map that takes t and returns the integral of u of ft, the m. This is continuous in 0 plus infinity absolutely continuous on the open half-line with derivative this is equal to minus u second dft squared relaxed gradient. All right, let's prove all of this. Okay, the first is trivial. In fact, all of these are trivial, but let's do one at a time. So the integral, notice that the integral of ft, of course, that's the same as, you know, actually, first of all, let me notice that the map that takes t and returns, well, put this way, yes, the integral of ft dm, this is the same as, you know, the scalar product between the function 1 and ft in L2. Right. No? The mass is fine. M has finite mass, so the constant one is in L2. This makes sense. And now this curve as a curve in L2 is continuous and absolutely continuous on the half line. So the same is true for this map. Okay. So if I want to prove that this map is constant, it's just sufficient that I prove that this derivative is equal to 0 almost every. Okay. So let's compute this derivative. So who is this derivative? Well, let me look at this expression. I can certainly, you know, drop the derivative in here. Right. So this derivative is equal to 1 dot Laplace in FTD. Right. And now I call into play this weak integration by parts formula that we have seen last time. Remember that we proved that the integral of G Laplacian f, you know, this was less or equal than the integral of relaxed slope of f, relaxed slope of G, whenever f is a Laplacian and both f and g are in the domain of the Gigli energy, right? But the constant function 1 certainly is in L2, and certainly is in the domain of the Gigli energy, you know, with 0 energy, right? So all constant functions, as far as the reference measure is finite, constant function certainly belongs is Lipschitz, you know, and certainly, you know, it has 0 minimum Wickham gradient, right? So this is 0. Make sense?
Nicola, sorry.
Yes.
The camera doesn't move to the right blackboard somehow. To the one on the right, it doesn't show it.
Ah, yes. So let me see if I can handle this by myself. I'll try. Let me put this.
Okay, good. Yeah.
Okay, I've done it. Okay. I was just recalling the weak integration by parts formula that I proved last time. So in proving that so if you are bothered by the fact that I've been a bit sloppy in this approximation via Lipschitz function, sometimes I said that I want to approximate with Lipschitz function with bounded supports, sometimes just with Lipschitz function. So if you're bothered by the fact that, okay, how do I approximate a constant function that has not bounded support in my setting, you know, in order to approximate the Gigli energy? If you're bothered by this, think that the space is compact. Okay, things can be. I mean, I'm slightly cheating over here. You know, I'm being a little bit low, but the space is compact. There is no such issue. Okay. So first, now second, okay, the proof of the second property is trivial if you know, one thing about how this flow is constructed that I've mentioned the other time, and this flow is constructed, of course, I mentioned without proving, so I'm asking you to believe me. So how do you build this flow ft? Well, you start from your function f, you fix a parameter tau bigger than 0, and then you recursively minimize. You first define, f tau 0 to be your given f, and then you define f tau, say n plus 1 to be, the minimum, the arg min of the energy, in this case the Gigli energy, plus distance squared from the previous guy, L2 divided by 2 tau. Okay, we have discussed this in the case of RD for functions on RD, that basically defining this sequence is in a sense solves a kind of time discretization of the gradient flow equation. And when tau goes to 0, if you properly rescale time over here, you are converging actually to the gradient flow. Okay. I'm mentioning this, so I mentioned this without proof, but just for you to know, basically, that if I'm able to prove that the weak maximum principle holds at this discrete level, then it passes to the limit. Okay. Of course, if you don't know that this converges to the gradient flow, there is still sometimes a hole in the proof, but at least this should be a convincing argument that this should be true. Okay. So let's see why this is the case. So now what I want to prove is the following: f as a bound from, say, below. Okay. Tau is a positive parameter fixed. I minimize this function, and my claim is that the minimizer, which is clearly unique, right? Because this guy is convex, the Gigli energy, and this guy is strictly convex. This is yet to know. Okay, so a strictly convex function can have at most one minimizer, right? And the minimizer exists because this is lower semi-continuous. Convex lower semi-continuous means weakly lower semi-continuous. This is also weakly lower semi-continuous, and these sublevels must be bounded, right? Because if you go far from F0, this term increases. Okay, so any minimizing sequence lives in a bounded set. All right, so let me say that f is greater or equal than some constant almost everywhere, and let's pretend that by contradiction assume that the minimizer, let's call it f tau 1, is strictly smaller than C somewhere on a set, on some positive measure set. Okay. So what is it? Let me draw a picture. This is the threshold C. Here is my function f. So here is my threshold. F stays above this, and then f tau, for some reason, f tau drops below this sublevel at some point. Okay. Now I want to build, by contradiction, I want to build a better, another function which does better than f tau in minimizing this guy. And what it is that I do? Well, certainly, simply I just truncate f tau. And I say that it has been unwise to go below this level. So I define G to be just the max between C and f tau. Yeah. So if G does strictly better than f tau, I'm done. Okay. Now, of course, the L2 distance between G and F is less or equal than the L2 distance between f tau 1 and F. I hope this is clear from the picture. F is above C, f tau is below. So if I increase a little bit f tau, that's true. In fact, this is strictly less. Okay. What about the energy? Well, first of all, is G Sobolev? Yes, it is, because G is obtained by f tau by post-composing with the function that is the one Lipschitz function, which is, I don't know, this is identical equal to C, and then is this is phi. G is equal to phi composition after 1. Right? Phi is one Lipschitz, and we have already proved that if I post-compose a Sobolev function with one Lipschitz, I remain Sobolev. So at least G is Sobolev. And what about its weak upper gradient? Well, on the region, on the set where f tau 1 is strictly smaller than C, we have that G is identical equal to C. Right? But we also know that if two Sobolev functions agree on a Borel set, their minimal weak upper gradients agree on the same set. So G agrees with the constant function, which has 0 gradient. Okay. So on this set, the minimal weak upper gradient, the minimal relaxed slope of G is identically 0 on this set. Right? And what about on the other set, on the set where f tau 1 is greater or equal than C? Well, on this set, G and this function agree. So the minimal weak upper gradient agree for the same reason that I've just discussed. Right? But then I'm done because the energy of any function is just the integral of the squared relaxed slope. Right? So the energy of G is just the sum, let me say, is the sum of, so let's give a name. So this is A. Is the integral over A of dgr squared plus the integral over the complement of A. All right? But this is 0. And this is the same as the integral of the relaxed slope of f. But for the relaxed slope of f, f pays in principle, or could pay something also on A. You see what I mean? So this is less or equal. Make sense? Of f2. Does it make any sense? Okay. It could be that also f2 has 0 weak upper gradient on this set. I'm not stating otherwise. But certainly we have already earned something at this level. Okay. So that proves my claim. And if you believe me that this, so in particular, this is stable, you can iterate this, this is true for f2.1, f2.2, f2.3, etc., and for any tau. So, okay, it's almost like the proof. Of course, I didn't prove the convergence of the scheme, but, I won't. Okay, now it remains to prove this last statement about this entropy dissipation. I will only use this statement for U equals Z log Z, but this is very general. So let me prove 3. So first of all, if let me prove this statement over here. Why this map should be continuous? Well, this is by dominant convergence. If ft goes to ft bar, when t goes to t bar, ft goes to as t goes to t bar. This is true in L2. Okay. In particular, let's say every subsequence has a further extraction that converges almost everywhere. Now the integral, now u of ft is bounded. By the previous step, once I know that f is between two constants, the same is true for ft. So first of all, this is well defined. Okay, u compose ft is well defined almost everywhere, and it's a bounded function because u is a smooth function from a compact interval to R. So this is bounded, right? But what I know is that this converges, basically in measure, or if you wish, f u of ft. For every sequence t going to t bar, you have a further subsequence ftn such that this converges almost everywhere. You agree? Right? And if this converges almost everywhere, the measure is finite, and all these functions are bounded, then the integrals, I have continuity of this. Make sense? All right. So what about absolute continuity then? Well, let me compute the integral of u ft minus u fs dm. Well, this is bounded by the Lipschitz constant of u times the integral of ft minus fs dm, which of course is bounded by the Lipschitz constant of u times the L2 norm of t minus fs, right? Because m is probability, right? So if the curve ft is absolutely continuous on some interval, on that same interval, both composing with u preserves absolute continuity. Okay. Right. So let's compute this derivative. And again, as before, dt of the integral. Well, actually, so let me write this formula. Let me see. what should I do to convince you that this is true? So what it is that I'm using over here? I'm just saying, well, I could write here dTft. Does this make any sense? You could prove this, for instance, you know, by looking at difference quotients, and you know, u ft plus h minus uft divided by h, and arguing by pointwise convergence of subsequences. The fact that ft is absolutely continuous tells me that for almost every t, ft plus h minus ft divided by h, or actually, if you want, by using this limiting, actually, we can use this guy over here. So this converges in L2 to Laplacian of ft, you know, as h goes to 0 from above, right? So fixed t where you know, fixed t positive. Look at this limit, look at sequence of h, take a subsequence where this convergence is almost everywhere, right? So then you get that you have convergence almost everywhere of the integral. So this converges almost everywhere, you know, up to subsequences. This converges almost everywhere to u prime of ft, Laplacian of ft, just by you know, post-composition of real valued functions. You know, the standard chain rule. No? For almost every x, you have this chain rule. And then by an argument by dominant convergence, again, you can pass to the integrated version. Okay, make sense? And then, but this is true for any sequence of h, so this is true, you know, for the full derivative, right? So but once you have this, we are done, right? Because now I apply the other integration by parts formula that I proved last time. And the integration by parts formula was that whenever I integrate, if f has a Laplacian, and I'm integrating Laplacian of f against a function g, which is of the form, you know, phi composition f, here phi is u prime, then this is equal to minus the integral of the, you know, the derivative of phi, in this case is u second ft, and then I have the ft squared, which is exactly the formula that I wrote. All right. So end of the proof. All right. So this works extremely generally. You know, we have used just the basic calculus. So there is no miracle in what is happening over here. Basically, what happened is that we've defined the Laplacian as this variational approach to Laplacian, so a subdifferential of the Chigre energy. And from there to all these statements is basically just, you know, algebraic manipulations of this property. So that approach to the Laplacian gives for free all this. Here it comes a theorem, perhaps the most important theorem about Sobolev functions that I've mentioned so far. Perhaps the only theorem, basically. So that's the difference between proving theorems and playing with definitions. So this is a theorem. It goes by the name of Cuvada's lemma. This has been proved. This has been proved by myself, Cuvada, and Ota, and in our paper on Alexandro spaces. But the basic idea has been, you know, is due to Cuvada, and so in agreement with Ota, we decided to call this Cuvada's lemma, and this has been later, you know, used by Ambrosio, myself, and Stavare in our studies about CD spaces and gradient flows, and the heat flow of that. But you know, the proof, I mean, this is really, it comes really from it. And here is the theorem. Same assumption as before. So M in particular, this. Take the space compact if you wish, if that helps you. And say that the initial density F is actually is a probability measure, is a probability density. So this guy a priori is in L2, right? But let me also assume that it's a probability density, with say less or equal than some constant. Okay. Then by what we know, what we already proved, then we know that let me define mu t ftm. I know that this guy is a probability measure with finite second moment. Why? Well, first of all, if this is a probability density, means that it is greater or equal than 0 almost everywhere. And so also ft is greater or equal than 0 almost everywhere by the weak maximum principle. Now, this is also by assumption less or equal than some constant. So also ft is less or equal than some constant. Therefore, given that this measure has finite second moment, the same is true for this. What about the mass? Well, I just proved that the mass is perturbed, so ft is mass 1, so this is a probability density with finite second moment. Okay. Now, Quadra's lemma tells the following: tells that t into mu t is, let me say, continuous with values in 0 plus infinity, and absolutely continuous in 0 plus infinity with respect to the Wasserstein distance W2. And I have a sharp control on the metric speed. This is bounded from above by the integral. Let me exaggerate a little bit. Let me also say that this is it's also bigger than some constant, so I have easier time writing this. So the squared Wasserstein speed is bounded from above by what is called Fisher information for almost everything. I will skip for a moment the proof of this fact and want to show you how powerful it is by showing the conclusion. But first, let me comment on the statement. So up to 1 second ago, all that this heat flow was doing, or gradient flow that Gigli energy was doing, was related to properties, in some sense vertical properties, vertical interpolation. It has to do with L2 functions and post-compositions with L2 functions. Now, Quadra's lemma tells that this guy, which is being produced by taking the gradient flow of the Gigli energy, in fact, is related in some way, and in fact in a sharp way, to the Wasserstein, to the optimal transport geometry. We can bound really the Wasserstein distance with the mu2 and mu s in a sharp way with the Fisher information. Okay. Of course, you can wonder why is this sharp, but this will be clear from the proof that I'm going to do now. Okay. So this is yet another link between the vertical interpolation and horizontal interpolation, if you wish, between the L2 world and the W2 world, between the Lagrangian side of the story and the Eulerian side of the story. Let me show 2 crucial consequences of this result. And then later on, I will prove this Quadra's lemma. Corollary. Basically the corollary is this: weak relaxed slope and a minimal weak aggregated coincides. In other words, more precisely, if F is in L2 and also in S2, then F is in the domain of the Gigli energy, and this equality holds. You might remember that during the last lecture, I proved that if F is in the domain of the Gigli energy, then it belongs to this space. And we had this inequality, which was basically trivial, right? Almost everywhere. Now I'm telling you that the other one is true. Make sense? Okay, let's prove this. Let me assume say for the moment that F is bounded from above by and from below by some constants. And let me think 1 second. Do I want yeah, and F say the integral one, so it's a probability density. Let me see. Then we discuss the general case, but once we settle the conclusion for this sort of functions, then the rest will be easy. Okay, then I build this gradient flow of the Gigli energy. Pick, Ft, a gradient flow trajectory of the Gigli energy starting from F. And let mu t be the Ft push forward Ftm. So this lives in P2x. Because I'm assuming for simplicity that M belongs, as finite second moment. If not, some approximation result has to be called into play. Let me think. Oh yes. Okay. First of all, let me look at how much. Let's have a look at the quantity integral of f log, or if you want, f naught log of f naught minus integral of ft log ft. The MDF. How much is this difference? Well, I'm really under the assumptions, f is bounded from above and from below. I'm post-composing f with a smooth function, which is z log z. So I'm really, in the setting of this entropy dissipation result that I've mentioned previously. So this is equal to the integral from 0 to t of the integral of the second derivative of z log z, which is 1 over z. So I have divided by fs, and here I have dfs relaxed slope squared, the MDS. Make sense? By the entropy dissipation for u of z equals z log z. I should have the difference, the derivative, dt of the integral u of t is equal, you remember, minus u second Laplace dft squared. Right? Now the minus here is is taken care because I did energy at time 0 minus energy at time t, and u second is 1 over. Okay. Okay, on the other end, this is less or equal, for trivial reason, let me write it in query and then we comment. This is less or equal than u prime of f naught times ft minus f naught. Here I just used the trivial inequality that tells that if U is convex, U of B is greater or equal than U of A plus U prime of A times B minus A. Maybe there's a minus somewhere for F not minus F0. Wait a second. U of B, U of A minus U of B is, yeah, maybe it's this. Okay, no, this should be okay. You see, A is F at time 0, B is F at time t, and this is basically the integral. So the integrated version of U of A minus U of B is less or equal than U prime at A times B minus A. All right. Okay, but now let me observe the following. Let me observe what? Well, let me first of all call. So this is the same as the integral of U prime of F naught. Let's say up to a sign, gamma naught minus U prime of F naught in gamma t d pi of gamma, where pi, for pi, lifting in the sense of the superposition principle of the curve T maps to mu T. Let me comment about this. Do I know? Let me think 1 second. I'm thinking whether I know already that this quantity is finite or not. Maybe I don't yet. No, surely do. Surely do. So in particular, surely do. So this integral in particular, say from 0 to 1, is finite because it's equal to the value of this guy minus f of 1. Okay. So in particular, so now let me look at Quadra's lemma. And let me notice, actually, let me write it here. So I have, so this curve is a continuous curve, right? Because Quadra is the limit. It is absolutely continuous with squared speed bounded by this quantity. But this quantity is in L1 of 0, 1. Right? The integral of mu t dot squared from 0 to 1 dt is less or equal than the integral from 0 to 1 of this Fisher information, which is finite because it is equal to this quantity. Right? So it makes sense. So in particular, this curve not only is absolutely continuous, let's say, on the open interval, but this is, this is in, AC of the interval 0, 1 with values in this Barstein space. We square the speed, which is in L1. So the speed is in L2. So I'm really in position to apply the superposition principle and lift this curve to a plan pi in the space of continuous curves with and I know that the integral, pi has the following two properties. Et for pi is mu t, and the integral for every t in 0, 1, and the integral of gamma t dot squared d pi gamma is equal to mu t dot squared, for almost every t. Make sense what I'm saying? The superposition principle tells you that whenever you have a curve of measures which is absolutely continuous with speed in L2, you can lift it. You can lift it to a probability measure in the space of curves that it has the correct marginals and it has the same kinetic energy. Right? So this I can do. So there is such pi, it's not unique in general, I don't care. There is such pi. I pick such pi and I plug it here. Okay? And now what is that I observe? I observe that pi is a test plan, actually. And by the way, this trick of lifting probability measures is the only way we will ever build the test plans. So this condition, if I integrate between 0 and 1, and I use this guy, I see that the plan has finite kinetic energy. Right? So the kinetic energy, no? The double integral. This is equal to mu t dot squared dt, so it is finite. And what about the marginals? Et push over pi, well, this is equal to mu t, but this is equal to ftm, which by the maximum principle is less or equal than a constant m. The same constant that was true for f at time 0. Right? So pi is test. Pi is test, and the function u prime, so pi is test. And the function u prime composed f naught is in the Sobolev class, you know, in this space, because f naught is in this space, and I'm post composing f naught with a smooth function that is smooth in its image. So by the calculus rule that we've seen the other time, you know, this is true, right? So I can so by the very definition of Sobolev functions in the sense of weak upper gradients in duality with test plans, I can bound from above this guy. This quantity is less or equal. Let me continue over here. This is less or equal. Then what? Then the integral from 0 to 1. Let me say the integral of the integral from 0 to 1 of the weak upper gradient of u prime composition f naught at gamma s dot ds d pi of gamma. And here I'm integrating from 0 to t, right? Because this is gamma t, right? If you want, I'm using, I'm starting from this plan pi, and then I'm restricting it to the interval 0 t. Here, this is extra operator, right? So I have this. Let me apply Young's inequality. This is less or equal than 1/2 the integral of the integral from 0 to t of d u prime composition f naught squared at gamma s ds d pi plus the double integral of the kinetic energy. I'm almost done. Then we take a break, but let me conclude the proof. Okay? But now I know who is this guy, right? This is the energy of the plan. This is exactly the speed of the curve. And I know how to bound the speed of the curve. Kuvada is telling me. So, I mean, the inequality goes in the correct direction. I can replace this with the integral from 0 to t of this relaxed slope fs squared divided fs ds dm. Okay. And who is this guy? So u prime is log, right? U was or log plus 1, whatever. No? The derivative of log is, again, I get a u second. This is so this is dfs weak squared divided by fs squared, because there is a square, right? So let me wrap everything up. Let me write it, say here, what I proved. What I proved is that the integral, this integral from 0 to t of the integral of dfs relaxed squared divided fs dm ds this is less or because this is equal to this difference in entropy, but the difference in entropy is bounded from above by this quantity. So this is less or equal than 1/2 the integral of the integral from 0 to t of the original f, weak squared. I will correct that in a second, times, and then I have, if you want, well, let me write this way: s the m plus the double integral of the same content that I have. So the s weak squared fs ds dm. So this was u prime composition f0, so this was f0. No, there is no s in it. Okay. And when I compute this function in gamma s, and then I integrate in the pi by the the rule of the push forward, this is the same as integrating this function times fs in the end, right? Because the push forward, the s marginal of pi is fs dm. Okay. So all this work allowed us to put the weak derivative on the right hand side of the inequality. You see, now this quantity is the same as this quantity. Here there is a 1/2. So let me erase this guy. And then we put a 1/2 over here that then simplifies. What we get is this. Okay. And now we are done. Because what happens? When s goes to 0, let me divide by t. Let me take the average. This is in L1. Because this quantity this quantity in assumption was in L2, I squared it is in L1, and I'm dividing it by a function which is bounded from above from below. So this quantity is in L1. These are uniformly bounded functions by the maximum principle, and they are converging in L2 to f. But so up to subsequences they converge almost everywhere. So this quantity converges to this guy when s goes to 0, when t goes to 0, sorry. This quantity, you can rewrite it as this quantity is nothing but 4 times the Gigli energy of the square root of fs by the chain rule. Right. So now the fs are converging in L2 to f, uniformly bounded. So also the square root of fs is also converging in L2 to the square root of f. In general, this is of course totally false, but in this case, we have uniform bounds from above and from below. The reference measure is a probability measure. So convergence in L2 is the same as convergence in every LP once you have a uniform bounds from above and from below, right? And if this is true, by the lower semi-continuity of the Gigli energy, you know that the Gigli energy of the square root of f is less or equal than the lim-inf of the Gigli energy of the square root of fs. And the same is here, we take the average integral, by phi2, the average integral between 0 and t. So the conclusion is that the Gigli energy of the square root of f is less or equal than this quantity. Right? In particular, square root of f lives in the relaxed Sobolev space. So to say, f is bounded from below. So now I can, say that the Gigli energy of the square root of f is equal to this 4 times the Gigli energy is equal to this. This makes sense because now I know that f, if the square root is in the domain of the Gigli energy, the square also is so, because the square root in a way is bounded. Right? So I can write this, and I know that this is less or equal than the integral of the f weak square divided by f. Okay, but of course I knew that point-wise this guy was less or equal than this almost everywhere. So after integration and multiplication by functions that are positive, I'm done. You see? So that's the line of thought. Uses basically all of what we have learned so far on Sobolev functions. Of course, this concludes the proof under this, also under the assumption that f is bounded from below, from above, from below, and is a probability measure. But you can easily reduce to that case, by first truncating and if necessary adding a constant, and then you let the truncation and then go to from. I mean that's the core of the argument, and the rest is simple. So let's take a break, 5 minutes, and then we continue. Time is, I want to prove that f is also positive. I pick this and I show that this also solves the equation. So if this is also a gradient flow, I'm done, right? Because it starts from the same guy. By you, is this what you were telling?
So what I want to do, yeah, for instance, because this is the composition with the function with
yes,
but as different bit.
Yeah, I don't know. So you should work a little bit. So of course, this what you can prove without much work is that this derivative is equal to the positive part of this derivative, I think. Well, no, no, it's not like this. No, it's not like this. No, it's not like this. This is false. It's a little bit technical, I think.
But if I write then I write.
Sure.
One button.
Oh, just of the integral. Okay, I see what you mean. Then
by the energy.
okay. Ah, does it work so simple? But then phi is convex, and therefore this. Ah, makes sense. You're right. That's another way. Yes, that's true. That's another way. Yes, you're right. Did you think about this? Yeah. Okay, sure. So we have a better proof now that does not use the fact that the gradient, this flow is, the limit of the discrete schema. All right, thanks. Okay, I think we can start. So the first powerful consequence of the quadrat lemma is this identification between weak and relaxed slopes. So from now on, of course, I will never write any more R or W. Okay, and so the two spaces are the same. Notice in particular, that we gain this approximation result out of this theorem, which is a priori absolutely non-trivial. That is, you take a function that is, I mean, by definition, you take a function that is Sobolev in the sense of test plans. Well, then there exists a sequence of Lipschitz functions converging to it, such that the asymptotic Lipschitz constant converging to the minimal reduced slope. It's totally, a priori unclear how to, in some sense, where this sequence comes from. It will be a little bit more clear once we see the proof of Quadrat's lemma. This has to do with the Hopf flux formula and the Hamilton-Jacobi equation. But let me, postpone for a second this fact. Let me now prove one other thing. So because I still have a problem with the heat flow, right? Because I call the heat flow the gradient flow of the entropy with respect to the distance W2, and certainly now I'm willing to call heat flow also this gradient flow of the Cheeger energy. So of course now we'll prove that they are the same, and the proof is based, among other things, beside Quadrat's lemma, is based on the following observation. Well, lemma. And the lemma is the following. Let me say that X is compact. It's not needed at all, but let me just say that X is compact. And let's say that F is a probability density. Probability density with Lipschitz probability density. And let me say that f is bounded from below by some strictly positive constant. Infinite because it is Lipschitz on a compact set. Well, then I can compute f is a probability density. Of course, the entropy of the measure f mu, let me put, let me call mu is the measure fm. Of course, this measure mu lives in the domain of the entropy, right? Because it is absolutely continuous with the density such that, you know, f log f is certainly integral with respect to f because it's bounded, right? So it makes sense, given that it is in the domain of the entropy, it makes sense to wonder who is or a bound from above this slope. And this guy is less or equal than the integral of the something that looks suspiciously close to an object that we have already seen a few times here. Okay. With the here there is a Lipschitz quantity, not really a sober one, but you know. Okay. In particular, if the slope is you know, weakly lower semi-continuous, then the slope of the entropy is less or equal than 4 times the Chicken energy of f. You know, every time f is sorry, of square root of f. For any f in L2 with you know, non-negative, and the integral of f is equal to 1. Okay. Now you might remember that I gave you an exercise to, I don't know if bound from above or prove some equality concerning the slope of the entropy, and now we are approaching the solution of that exercise. So let's see. Proof. So mu is given. Let's say the nu is another probability density of the form integral of Gn. And let me, you know, I want to bound from above the entropy of mu minus the entropy of nu. Right? And this is, you know, this is less or equal than the integral, you know, as before, u of z is a z log z. And this is less or equal than u prime composition f times, okay, let me see the signs over here, times, I think it should be f minus g dn. It doesn't matter, but it should be this way. Okay, because this is again, this is the integral of u of f minus u of g. I use the convexity of u to get to this. Right? You agree? At every point, by the convexity of u. So I've integrated this and I get this. Okay. And then what do I do? I don't recall. Haha, yes. Let's now let alpha be an optimal plan between mu and nu. It exists. These are probability measures. There exists in a compact space. So certainly there is an optimizer for the you know, quadratic transportation problem. And so this guy is equal to the integral of u prime f in, I guess, x or y, whatever, minus u prime f at y and the alpha xy. All right. Which, okay, this is called, let me actually be a little bit more specific. This is log f minus log f. Okay. The +1 gets simplified because there is a minus, right? Okay, so this is less or equal. Then, okay, let me divide, if you want, let me divide and multiply by the distance xy times distance xy. And then what do? I do Hölder, Cauchy-Schwarz. This is less or equal than the integral of log f x minus log y squared divided by the distance squared xy, the alpha, times W2. Right? So now let me introduce a function. Let me call L of xy. This is the function which is equal to log fx minus log fy divided the distance between x and y if x is not y, and is equal to the asymptotic Lipschitz constant of f at x if x is equal to y. This is a function of two variables. No. If x and y are different, it's just this difference quotient, if you wish. Actually, let me put also the absolute value just in case, and I take and the asymptotic Lipschitz constant if not. Okay. Notice this is upper semi-continuous. Right? Because basically it is continuous outside of the diagonal because f is continuous. But if you approach the same base point, by the definition of of the lip divided by f. Sorry, I wanted to say the asymptotic Lipschitz constant of log f. So, yeah, sorry, I should divide by f of x. Right? Should log fx minus log fy divided distance xy in absolute value, and here is the the derivative of log fx, which I'm writing as the asymptotic Lipschitz constant of f of x divided by f of x. This coincides with the asymptotic Lipschitz constant of log of f at x. Okay? This is upper semi-continuous. Makes sense? This is upper semi-continuous. Okay, but if this is upper semi-continuous, now we have, so this is this is equal. So what let me rewrite what I just this previous computation that I just pointed out. So I just proved that the entropy of mu minus the entropy of mu is bounded from above by the distance between mu and nu in the sense of Bastien space times square root of the integral of L squared d alpha. Of course, this quantity is positive, so there's no harm in taking here the positive part. This is true for every mu and nu, basically. Or let's say, let's fix mu, and this is true for every target measure nu. So now let's write this for a sequence of nu's converging to our measurement in the Bastien sense. What we get, so write nu equal nu n equals say GNM, converging W2 to mu. Okay, then this is telling us that that the lim sup of the entropy of mu minus the entropy of nu positive part divided by the distance, this is less or equal than the lim sup of the square root of the integral of L squared d alpha n, okay, where alpha n is optimal between mu and the measure nu n. It's the same, I've done nothing, right? Okay, but what's the point now? The point is that if mu n is converging to mu, of this plus alpha n, this will converge weakly to the identity comma identity push ordinate. I mean, in the limit, they won't change anything. Now, if f is as in the assumptions, this L of f is upper semi-continuous and bounded from above. L was Lipschitz, far from 0, so there is no problem in this. But so we have an upper semi-continuous, taking the square, of course, of a positive function, preserves upper semi-continuity. So I have an upper semi-continuous function, and the sequence of measures converging weakly to a limit measure. So of course, this is less or equal than the square root of the integral of L squared d, identity comma identity push ordinate. Right? Which proves this, right? I'm done. Right? Because L squared in this measure, this is the same, the square root. No, identity, this is concentrated on the diagonal where L is equal to this. So this is equal to the integral of Lipschitz constant asymptotic of f squared. I should write divided f squared integrated in d mu. But mu carries an f in some sense inside, right? So one f at the denominator disappears, and that remains with the integration with. Okay. How do I pass? So that's proved. Now from here to here, this is trivial, right? Because no, there is something. Is that okay? Makes sense? Okay. So from here to here, what do I do? Well, basically, what I want to do is look, I pick my arbitrary function f, and I approximate the Chigger energy of square root of f. There exists a sequence of functions, of Lipschitz functions. Let me call them square root of fn. These are converging in L2 to square root of f, with the asymptotic Lipschitz constant of square root of fn converging in L2 the minimal weak upper gradient of f. I don't write RW. Okay. Well, but now you see this guy is positive. So these guys certainly I can think them positive. There is no need of taking, when approximating a positive function, if I truncate, I can certainly assume that the approximating sequence is also positive. And I can certainly add a little bit of a constant that goes to 0 in order to be sure that each of these is bounded from below by a positive constant. These are Lipschitz, so in a compass set, they are certainly also bounded from above. There's no problem. And in adding this little constant, this I will not perturb too much. So basically, what I'm doing here, I'm concluding by passing to the limit, in the right hand side, using the fact that the left hand side is weakly over semi-continuous. If this is true, in particular, the square root of fn m weakly converges, in particular, to square root of fn. What am I doing? Sorry, fnm weakly converges to this, in particular, because it converges in L1. Right? So by approximation, using basically I put the assumption in such a way that this is true, that I can approximate. Okay. All right. By the way, this computation of the slope in the metric setting, I think, at least in the Lipschitz case, I think has been done first by Villani. You should find it in his book, Optimal Transport All the New. Then the relaxation part comes from my paper with Cuvada and Dota. Okay, now here is the theorem. It's more of a corollary of Cuvada's lemma, but this is important, so let's take this as a theorem. This comes from the paper with Cuvada and Dota, and the generalization so with Cuvada and Dota we only worked on Alexandrov spaces, but the generalization to general metric measure spaces is basically trivial, at least once one knows a little bit something about the Hopf-Flux formula. That we discuss this in a second. Now the theorem is this: let x dm be, okay, let me exaggerate here, compact is absolutely not needed, but just CD K-infinity spaces. Okay. So what we know about this space by the definition given by Sturm-Villani is that the entropy is K-convex, right, in the Varsenai world. Now let mu equal Fm be, you know, a probability measure with finite second moment. With F in actually in L2, so not only L1, but actually is in L2. Now we have two ways of flowing this. So we can consider the curve T into Ft be, you know, the gradient flow trajectory of the trigger energy with respect, you know, to the L2 distance, starting from F. That's, you know, the heat flow in the sense that we have discussed today. Right? And also let T into mu T be the gradient flow trajectory of the relative entropy with respect to the Varstein distance W2, starting from mu, assuming it exists. Okay, we prove the uniqueness statement of this, but there is at most one of these. Say that there is one, then mu T is actually equal to FTM for every T. Okay, so these two heat flows actually coincide whenever they can coincide. One is a flow of probability measures, the other one is a flow of L2 functions. But if I start from a guy which is both a probability measure and an L2 function and they flow, then they agree. Okay, to be a little bit more precise, given that I did not show, I only showed uniqueness for at the level for the gradient for the relative entropy. I can formulate this theorem in an equivalent, you know, not in a weaker sense, by saying, look, if I take this gradient flow trajectory and I define mu T in this way, then this is a gradient flow of the relative entropy. No, because this guy exists. No, FTM exists. You get it from the gradient flow theory of converse functional Hilbert spaces, so it exists in a sense in an easier way. Okay, so you define mu T. This happens to be a gradient flow of the entropy. In fact, this is our proof. Now, given that the gradient flow of the entropy is unique, that's the only one, right? And in particular, we have proved the existence, you know, of this guy by, you know, in some sense, by doing some, you know, by in a very not direct way. Okay, so this now this so we have what I comment. So we have seen that the optimal transport point of view gives more or less for free. I mean, once you write down the definition, gives you more or less for free the stability of this gradient flow with respect to, you know, convergence of basic spaces. Okay, because of the loss to Milan stability result and my stability result for the gradient flow. Okay, so optimal transport gives stability of this. This theorem is telling you that this gradient flow is the same as the gradient flow. So in some sense, from this statement, it should follow that the Laplacian basically converges along a sequence of spaces. And if the Laplacian converges, well, you know, you are in a very good spot for passing to limiting basically whatever differential identity or inequality you happen to handle. So this is basically the root of the stability of differential quantities in the CD or RCD setting is based on this. Okay, this identification plus the stability of the system. All right, let's prove this theorem. Okay, now this theorem is surprisingly, with all this work that we've done so far, the proof is surprisingly simple. Because let me define, mu T via, star. Okay, let me forget, in some sense, let me forget about this line if you wish. Let's forget. I define mu T in this way. If I prove that this guy, satisfies our definition of gradient flow alla De Giorgi, then we're done. Because we knew, no? We already proved that this gradient flow of the relative entropy is unique, right? So the aim is to prove that the entropy of mu0 is the same as, actually, I should put it this way, is the greater or equal than the entropy of mu t plus 1/2 the integral of mu s dot squared plus the slope squared of mu s, right? For everything. You remember? Because the other inequality is always satisfied. So if I get this, I get a gradient flow, and it's sufficient to check this with mu equals 0. Okay. Now let me write 3 things that we know. On one side, we know that this guy is equal to minus. Okay. Let me assume. Let me assume. That mu0, you know, that if you want that f, as usual, is bounded from below by a positive constant and bounded from above by another constant. For simplicity, then, I mean, if we can conclude under this assumption, then if you want the stability of the gradient flows in both cases, you know, both in the L2 sense and the reverse sense, we can conclude. So let me just allow me to be a little bit lazy and assume make this assumption. And then notice that we do know that this holds. We do know that this holds. Actually, let me write this way. The minus this is less or equal than the same quantity, and also that this law of the entropy is less or equal than the same quantity. So we know that the entropy, you know, the map that takes t and returns the entropy of mu t is really the same as the map that takes t and returns the integral of ft log ft. No? And we've already seen that this map is absolutely continuous with derivative that is given by this expression. Right? So this we know. This is Quadra's lemma. And this is the statement that we just proved. If you remember that under the assumption of K convexity, the slope is actually W2 lower semi-continuous. So in particular, also you know, weakly lower semi-continuous. You know this? So K now because you can write the slope as a sup, right? Not as a lim sup, and therefore it's lower semi-continuous. Right? So these 3 together give the conclusion. The entropy times 0 minus the entropy at time t is the same as the integral from 0 to t of this expression. But this expression bounds from above both the speed and the entropy and the slope of the entropy. Okay. And by the way, this is a further confirmation that this inequality in Quadra's lemma must be sharp for most everything because there's no room of getting a strict inequality. But this perhaps was clear also from the proof of identification of the relaxed slope and the weak amplitude. Makes sense? I mean, there's nothing else to be done. It's done. Okay, I should discuss what happens if my original density is not bounded from above or from below. And what I would do, I would truncate and be sure that everything passes to the limit. And everything does, because basically at the right hand side we have something which has the tendency of being lower semi-continuous, right? The slope is lower semi-continuous. This is a Varstein speed. The Varstein speed tends to be lower semi-continuous with respect to weak convergence. No? The entropy is passed to the limit. Plus details, but you know, already for positive initial datum, this is, you know, quite strong. Make sense? So that, you know, so we basically have now, okay, I have to prove the lemma of Quadra, but basically now we have all the tools to really start, you know, making serious analysis on CDK infinity spaces. We have this identification, these 2 words now communicate L2 and W2, they communicate in a very strong way. Okay. Okay. It remains to prove Quadra's lemma. So which is you see the corners. So this is where I start with something related, L2 related, and I prove something W2 related. Okay. So this is where the magic happens, if you wish. And I will. So I don't think so today. I don't think I will have time to prove this. But at least let me show you how to reduce proof of quadruple lemma to another statement, namely this Hopflux formula Hamilton-Jacobi equation. Let me give a definition. So for a given, so if you have a function x on your preferred metric space values R, and you have t positive, let me define qt of f at the point x. This is the Hopflux formula, inf convolution, Moreau-Ursid approximation. There's a lot of different names, and this proves, of course, that this is quite an important thing. So let me take the inf over y's of f of y plus the distance squared between x and y divided by 2t. This is a formula. Okay. Now, if you have a little bit of familiarity with PDEs, first order PDEs, and Hamilton-Jacobi equation, you know that this is called the Hopflux formula in RD. And perhaps you know that this formula provides the unique viscosity solution of the Hamilton-Jacobi equation with initial datum f, at least under appropriate assumptions on f. Interestingly, this concept of viscosity solution, is retained. It can be pushed if you want, even to the metric setting. I don't want to go that far. For me, I'm satisfied. I will be satisfied with the following statement, which in this form, I think this goes back to my paper with Ambrosio and Savare. But there are, I should quote other colleagues. Okay, now I don't remember the names. On Friday, I will. There are other names to be added here. Let me just point out so that on PI spaces, this was known on PI spaces. This was also observed by Lotte and Villani, more or less. This statement. Okay. Anyway, the statement is this. So let's assume that f is Lipschitz and bounded on x. You start with a function which is bounded. Of course, I mean, here, if I don't put assumption, it could be that this inf is identically minus infinity. No? Let's say that the function f is unbounded from below in a very bad way. But let me say that I start from a Lipschitz bounded function. Then the map that takes t and returns the QTF as a map, takes value in the space of continuous bounded functions, is Lipschitz. I mean, where in the target space we take the sup norm, and for every x in x, if I look at the curve, of course. So now, if I put the sup norm here, and I'm telling you that this map is Lipschitz, it means that for every x, the curve that takes t and returns QTF at x is Lipschitz, right? But what I'm telling you is that dt of QTF at x plus the asymptotic Lipschitz constant squared of QTF at x divided by 2, this is less or equal than 0. Let me say for almost everything. I mean, I could say more than this, but let me just be content with this. Do you have a question? Okay. So you see, up to these, inequality on RD, this would be an equality, and here you would have grad QTF squared. If you know about the Hamilton-Jacobi equation. So in some sense, this inequality is retained even in the non-smooth setting, in the metric setting. Okay. Now, what I do today, I conclude by showing how this proves quadratus lemma. So then on Friday, I will just stick to the Hopflux formula that, by the way, has nothing to do with reference measures. This is a statement of metric spaces. There is no measure in there. Okay. Okay, so let me repeat the statement of Quadra's lemma. So, given that I stated it maybe 1 hour ago, so we have a metric measure space with M, the reference measure, which is a probability measure with finite second moment, bounded second moment on X. Okay, we start from a probability density, which happens to be bounded from below and from above by positive constants. It was strictly positive. Okay. I take the measure as I take the gradient flow trajectory of the Chigger energy starting from F, and I define these measures mu t. And the statement of Quadra's lemma is that the map that takes t and retards mu t is continuous on the Boole half line and absolutely continuous on the open half line with respect to the Barcelon distance, with this precise estimate on the space. Okay. Now, the continuity estimate is trivial, because Ft is continuous in L2 up to 0. The space, the reference measure M is finite, so continuity in L2 implies continuity in L1, which implies weak continuity in the sense of measures. There's the second moment are uniformly bounded. There is nothing that goes wrong in there. If you want, take if you are bothered by the difference between weak convergence, W convergence, just say that the space is compact. So that's not really the point. Now, the hard point is in this and this estimate. So let's have a look at this. So proof. So pick at t strictly positive, s bigger than t, and we need to estimate from above this guy. Yeah, from above. And how can we? So here we have a situation where, how to build an optimal a plan, admissible, optimal. A priori, we have no idea. And the trick is to use the dual formulation. So this is the same as the sup over phi, let's say continuous and bounded, actually Lipschitz and bounded, of the integral of phi, what is this, d mu t, plus the integral of the C transform of phi d mu s, where C for the cost function, which is distance squared over 2. This is the dual formulation. Okay, why Lipschitz and bounded? By an approximation argument. A priori, I said no among all phi's, but let me just by approximation can do this. And now, what this has to do with the Hoplux formula? Well, this is the same as the sup among psi that are Lipschitz and bounded of the integral of q1 psi d mu s minus the integral of psi d mu t. Think psi to be equal to minus phi, and notice that if you recall the definition of C transform with this cost, you have that q1 of minus phi is the same as phi c. So there is just algebra here. All right. And why this makes our life easier? Well, because now if I want to bind from above W2 squared between these two measures, it's just sufficient to bound from above this difference for any psi. Right? And now notice, so let me rewrite once again what it is that I want to bound from above. I have q1 psi d mu s minus the integral of psi d mu t. Okay, which let me write it in a different way. I mean, it's q1 psi fs minus psi ft dm, right? By the definition of mu s and mu t. Okay. Now notice that by construction so the map that takes t and returns ft actually, let me put it this way, R and the term FR is, absolutely continuous on the interval TS with values in L2. Because it's a gradient flow trajectory. So on that interval, it's absolutely continuous. And the map that takes R and returns QR psi is, by this lemma, is absolutely continuous with values, from 0, 1 with values in CB, but then, a fortiori with values in L2. No? M is a probability measure, right? So if I have a bound on the L infinity norm, it's a bound on the L2 norm. So, right? Okay, but therefore the map that takes R and returns FR times QR psi, this is absolutely continuous with values, T with values in L1. That's I have two curves with values in L2. I take the scalar product of these two guys. I get something which is okay. So this guy is equal to the integral from 0 to 1 of the derivative in R of what? Of the integral. Okay, now I should pay a little bit of so QR psi f at time 1 minus R t plus RS. This is integrated in the M, the R. Right? No, because in some sense, so this is so at time R equal 1, this guy is equal to this. At time R equals 0, this guy is equal to this. And I have enough regularity by either gradient flow theory or this statement about hot flux formula, and I forgot, I guess, okay, but also okay, and we can write this. Okay. Now again, so when I differentiate, if I have to differentiate, if a VT and WT are vectors on a Hilbert space and they want absolutely continuous in time and I want to differentiate, the Leibniz formula is in place, right? Right? For absolutely continuous curves on a Hilbert space, right? So I apply this Leibniz formula here. And what it is that I get? Well, this is equal to the integral, double integral, say 0, 1. If the limit drops in here, I have the R QR psi, and then I have F blah, blah, blah. And then I have plus, I get a factor S minus T because of this rescaling, QR psi, dr of F, blah, blah, blah. Make sense? Okay. Subini, this derivative is bounded from above by this guy for almost everything and for any x. So I swap. This is certainly bounded from above by the integral, from 0, 1 of the integral of lip minus lip a squared q r psi divided by 2 f 1 minus r t plus rs. The inequality is, so f is non-negative, so I'm not destroying the inequality by multiplying by f. Okay. And what is this guy? Then I have plus s minus t q r psi Laplacian of f at 1 minus r t plus rs d m dr. Make sense? I've done nothing, just applied Leibniz formula. Weak integration by parts for the Laplacian. This guy, this guy is less or equal. Then, okay, the integral from 0 to 1 of the integral, I keep the first guy, lip a squared q r psi divided by 2, f at 1 minus rt plus rs. And this guy, what do I get? I get a plus s minus t, minimal weak upper gradient of qr psi, minimal weak upper gradient of f at the indicated point. Make sense? All right, let me let me divide by the square root of f, multiply by the square root of f. And now I apply Young inequality. I split, so I give this guy to this factor and a square. So this is less or equal then, let's look what happens. Minus lip a squared q rho psi divided by 2 f at this point, this time. And then I get a plus 1/2 the minimal weak upper gradient of q r psi squared f plus s minus t squared over 2 the minimal weak upper gradient of f squared divided by f, the MDR. Make sense? Huh? These times square root of f squared times 1/2. You know, this guy makes sense. This guy, this is this, and you know, this guy is this. Okay. But now we are saying a compass space, f is non-negative. This is the relaxed slope, and this is the absolute probability constant. Clearly, this quantity is bigger than this. QR is Lipschitz. Okay. If you want, let me add this now. QR and Lipschitz. QR is Lipschitz. Okay. Let me add to the conclusion. So it's true. This Lipschitz, the minimum coupling is bounded from the probability constant. So I can erase these two, and the inequality is still true. And now I am extremely happy because there is no psi anymore in here. This is true for any psi, which is unbounded. The difference above is bounded by this guy. There is no psi. So when I take the sup over psi, what I get, let me write here above, this quantity is less or equal, so this quantity is less or equal than s minus t squared over 2, the integral from 0 to 1 of the integral of df1 minus rt plus rs squared divided by f in the same dm di. Right? That's this guy over here that I copied over there. Okay. And I'm done. You see that? So that's already, you know, this quantity in particular, by the maximum principle, f at later time is always bounded from below by this constant. So, and I'm writing a bad inequality is less or equal than some constant, s minus t squared the integral, you know, of the minimal weak upper gate of f at this later time di, right? Yeah. Okay. This is the energy. This is the Chigger energy. The Chigger energy of you know, f at later times. All right. But the Chigger energy of f at later times, you know, is bounded from above by the Chigger energy of f at the initial time. So this makes sense. So this proves that this is less or equal than constant times s minus t squared times the Chigger energy of f at time 0. Right? Okay. Which, okay, at least if f is Lipschitz is already bounded. Okay, otherwise I have to argue by approximation. Okay, and once you know, so this was the Wahrscheinlichkeit distance squared between mu at time t and mu at time s. This distance squared is bounded by s minus t squared times the number. So this proves Lipschitz continuity of this curve on this compact interval. Make sense? And once I have the Lipschitz continuity, this bound comes from, you know, I just proved, you know, I proved that 1/2, you know, if you want, I proved that 1/2 W2 squared mu t mu s is bounded by this quantity. So now you divide by s minus t squared, you let s go to t, and by a Lebesgue argument, by an argument on Lebesgue points, you do this. Okay, so you first have a Lipschitz bound just because you exaggerated a bit. You put here if you want. If not the Chigger energy at time 0, you can also put here the Chigger energy at time t, if you wish. Okay. Make sense? Right? And perhaps let me be a bit more precise over this step, so that I don't have to, to show you that I'm not cheating. So this is the interval from 0 to 1 of this quantity. Now the denominator is uniformly bounded from below. Let me put this constant over here, and let me put also the 2 in here. And here you have the interval between 0 and 1 of the energy of 1 minus r t plus rs. Okay, but so this is the same as c s minus t squared, the interval between 0 and 1 of the trigger energy of f at 1 minus r t plus rs dr. Okay, but for any r, this quantity is less or equal than the trigger energy at time t. Okay, because the energy decreases along the flow. Okay, and this is finite, right? I mean, this quantity is finite because at any positive time you fall into the domain of the energy. Okay. So now I proved that the curve is locally Lipschitz and with a sharp bound on the speed. Okay. So everything is reduced, and last time we start from this to the study of the hot flux formula and the Hamilton-Jacobi semigroup in arbitrary metric spaces. Okay. And that's all for today.